Hello everyone and welcome to today's webinar in the Serta and ESTCP webinar series. My name is Jennifer Nyman. I am a principal at Geosyntec Consultants in Oakland, California, and the coordinator of the webinar series on behalf of Serta and ESTCP. I will be facilitating today's call. The webinar will consist of a brief overview of Serta and ESTCP by Dr. Raman Analysis, followed by a list of upcoming webinars in the series. After Robin's opening remarks, we will transition to the technical portion of the webinar. Today's event features 3 speakers describing Serta and ESTC projects in the Weapons Systems and Platforms program area. Mr. Marc Whitehead of the Sherwin-Williams Company will begin the presentation describing novel coating systems for use as high-performance chemical-resistant powder top coats. His presentation will focus on Department of Defense requirements and coating development. Next, Dr. Jim Wynn of the Naval Research Laboratory will describe coatings characterization and analysis. His presentation will be followed by a brief question and answer session for both Jim and Marc. Finally, Dr. Beth Ann Pearson of the Sherwin-Williams Company will discuss coatings transition to the military market. Dr. Pearson's presentation will be followed by a second question and answer session. We will conclude with a question and answer session with all 3 speakers. Today's broadcast will be listen only. You may submit questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we encourage you to submit questions in advance of that session. On this slide, we have provided a few suggestions in the event that you experience difficulties with the broadcast audio. Typically, any delay will be fixed if you refresh your screen or call into the conference line. However, if you continue to have problems, please submit a comment using the chat box in the lower left corner of your screen. And with that, I would like to introduce Dr. Raman Analysis, who is a Serta and ESTCP Program Manager for Weapons Systems and Platforms. Before joining Serta and ESTCP, Raman worked at Navarre's Weapons Division, China Lake in California. Robin?
Thank you, Jennifer. I'm pleased to welcome everyone to today's SERTIP and ESTCP webinar. So, SERTIP is the Strategic Environmental Research and Development Program, and it was established by Congress in 1991 as a partnership between the DoD, the Department of Energy, and the EPA. SERTIP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. SERTIP funds both fundamental research as well as advanced technology development, which can ultimately impact real-world environmental management. ESTCP is the Environmental Security Technology Certification Program. In this program, we demonstrate the innovative environmental and energy technologies. These investments capitalize on past investments under SERTIP or other research programs, which are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. SERTIP and ESTCP are complementary programs, with much of SERTIP research and development occurring at the lab and pilot scale, with occasional field efforts, while on the other hand, ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted. There are 4 program areas in SERTIP and 5 in ESTCP. Energy and water program areas only in ESTCP, while the other 4, environmental restoration, munitions response, resource conservation and resiliency, and weapon systems and platforms, are SERTIP and ESTCP programs managed jointly by a designated program manager. Today's webinar is focusing on research and demonstrations that were conducted under the Weapon Systems and Platforms program area. This program area has 5 major focus areas, including surface and engineering, structural materials, energetic materials and munitions, noise and emissions, waste reduction treatment in DoD operations, and lead-free electronics. Okay, so our webinar series highlights research and development efforts from each of the 5 program areas. And as you can see, upcoming webinars will cover a broad range of topics, including high-resolution site characterization at chlorinated solvent sites, tools for risk-based remediation of unexploded ordnance, coupling geothermal heat pumps with underground seasonal thermal energy storage, future vulnerability to Alaskan ecosystems and tools for permafrost assessment, and finally, the management of energetic and propellant materials releases on testing and training ranges. You can find more information about upcoming webinars at the link on this slide. Registration is now live for webinars through the end of the summer. I would like to remind you all that a copy of today's presentation can be downloaded from our webinar page. We would appreciate it if you could please take a moment to complete the survey that will pop up on your screen at the end of the webcast. And I am very pleased to announce that for the first time since 2011, the Serta PSTS Symposium will be held November 28th through 30th in Washington, D.C. The 3-day event will showcase the latest technologies that enhance DoD's mission through improved environmental and energy performance. Registration information is available on the Serta and ESTCP website. I thank you and hope you enjoy today's webinar. Back to you, Jennifer.
Thank you very much, Robin. And it is now my pleasure to introduce Mr. Marc Whitehead. He is a staff scientist in the Sherwin-Williams Global Finishes Group Innovation Laboratory in Chicago, Illinois. His area of expertise has been developing coatings using innovative technologies for industrial applications. At Sherwin-Williams, Marc spent 20 years as the Technical Director for Military Coatings in the Products Finishes Division. He has several patents related to low-cloth polyurethane coatings technologies that focus on durability and low to no volatile organic solvent emissions. Marc has an Associates of Science degree in Petroleum Technology from the University of Pittsburgh. Marc?
Thank you. Marc Whitehead. I'm going to go over the presentation outline for the entire day, and DoD requirements and the coatings development will be what I will cover. So I will basically discuss how we came about the statement of need, and then we will pass it on to Jim Wynn, and he will discuss all the characterization that was done in the development of this coating. And then we will pass it on to Beth Ann Pearson, who will talk about how we basically are transitioning this to commercial military markets. So what I'll be focusing on are the DoD requirements and how we develop the coatings. So basically all starts with us establishing a team. And it's a good time for me to say that it was a big team effort between the characterization team, which was NRL and SUNY Stony Brook. We had a very interactive relationship with them and helped us basically get fundamental understanding of not only developing coatings, but how they really worked. We also have a really good relationship with our focus market group, so where Beth Ann's involved, we within Sherwin-Williams pass it on from the innovation lab into the basically powder coatings lab for military coatings. So that product now is in a commercialization lab. And we also work very well with Estron resin supplier. Without them, it wouldn't have been possible to develop a new powder coating. And then last, ARL writes the specifications, tests towards the specifications, and basically makes adjustments to specification as needed. So the requirements were set out in a statement of need for this product, and we are talking about a chemical agent resistant coating. So the requirements are the same as the liquid chemical agent resistant coatings. However, what had to be done was a powder coating specification was written. So powder coating specification being MIL PRF 32348. Type 3 is the exterior top coat, which equals the existing liquid coating. So when these things are applied, ideally you cannot tell the difference between liquid and powder. With that said, one of the statements of needs, we want it to be compatible with all current coating system applications, meaning pretreatments, primers, and the existing liquid Carc top coats. So if we're powder coating something at one location, we must be sure that we can put a liquid chemical agent resistant coating on top of that, so that there's no really change in the current practices people are doing. We're just adding to it. With that said, some adjustments were made where we did determine that some changes had to be made where you only use a powder coating under the powder coating top coat. So the liquid epoxy coatings that were out there as primers for liquid Carc were really not compatible with powder coatings, and that's a good representation of coatings manufacturers working with ARL and proving the point out, and then some adjustments made to the specification and the needs of the program. One of the key requirements was maximum cure temperature of 400 degrees F, so that this is compatible with many of the alloys that are used in military. And the one thing I'd point out that there's always been a need for a powder coating. People have been working on the powder coating for 25 years. Before I even worked with Sherwin-Williams, people were trying to develop a powder coating Carc. And this was not achievable. Nobody was successful. No one was qualified, and this effort basically made it a big commitment, not only on our part, Sherwin-Williams, but on ARL's part, and with some partners and resin suppliers. It really needed a long-term commitment. So we were able to accomplish in 3 years what wasn't really accomplished in 25 by making it a priority and putting efforts toward a concentrated effort. So the technical approach we did, our background was liquid Carc. We have a lot of liquid Carc experience. So where does this differ? I'll point out that liquid Carc has 30% solvent in it. So you have a combination of solvent, or 40%, and pigment and binder there. So you see equal parts, and we call it a pigment to binder ratio of 1 to 1 with 40% solvent. So these are typically high filler loading levels, and high filler loading levels typically make things less exterior durable, and they make things somewhat absorbent to chemical warfare agents. So we knew those were some of the weaknesses within liquid powder Carc, the high amount of pigment. So the strategy on developing a powder coating was to have a binder-rich system. So we're looking at 3 to 1 parts of binder to pigment, a lot less. So we're talking about low filler loading levels, and what this would lead to would be improved exterior durability and somewhat of a film that's more tightly formed, less filler pigments in there, so which sort of act as a wick in absorbing some of these agents. And we had some background on this. We knew that powder coatings could be made flat with lower loadings of fillers, but we weren't able to meet all the requirements of Carc. So how are we able to basically flatten with low levels of pigment? Well, the key here is that we use the resin to help flatten the coating. So this is basically a cartoon depiction of an incompatible polymer. So when the polymers are incompatible by themselves, they will have a low gloss on their own. So what was important was to use low gloss resin systems combined with flattening agents at a lower level to make the powder coating. It's something that is not done in liquid Carc. Liquid Carc resins are high gloss. So this was a fundamental knowledge that there was powder coating technology out there that could give you low gloss using resins. Not as low as chemical agent resistant coatings, but low gloss just by blending resins. But what hadn't been done ever was meet the chemical warfare resistance properties. So the chemical resistance was not there. And so what we had to do was work with the resin suppliers and improve the chemical resistance of these low gloss resin systems. This is a big fundamental thing that we did here. And what we really did within the program is we used clear resin systems to screen what resin systems would be worthwhile pigmenting. So it was a sort of a fast throughput way to evaluate things. So we would try to obtain good chemical resistance and low gloss in clears. So we basically made clear resin systems, check chemical resistance using methyl ethyl ketone, and if it touched the resin system, basically if it did any effect on it, by experience we knew that this would not make a coating system that would pass the requirements in the military specifications for chemical resistance. The other thing that we did is we needed to have ultimate a fairly low gloss clear coating. So there had to be what we call incompatibility. And so what we see in these depictions is what we were shooting for, to have one resin system inside the other, to have a resin system that lowers the gloss. And what we ultimately found out, and you'll see later, is created some surface roughness by having resin systems that were incompatible. So our approach was successful. We were able to get the low gloss needed for chemical agent resistant coating. So on the right here, we basically have a depiction of what we were able to produce with resin systems. So much like the ideal depiction in the cartoon, we were able to put, there are two resins on the right, and we basically have a domain, and we have a continuous film. So we have one resin system inside the other. This would be a low gloss coating in a clear coating. This helped us contain consistent gloss, and realistically, even though I said surface roughness was, some surface roughness is needed to get low gloss coatings, when you have a lot less pigment than liquid systems, you can get a very smooth coating for a low gloss coating. The chemical resistance, we screen with MEK solvents in the clears. Once we pigmented, this was sent for the official chemical warfare resistance testing. Results sent back through Army Research Lab, and we were able to pass all the requirements. So there is complete acceptance of all the data is performed by Army Research Lab, and we're happy to say we are on the qualified products list. So one of the other key requirements that we're trying to do when we're obtaining a low gloss coating is to have superior exterior durability. Low gloss coatings, chemical agent resistant coatings, have historically chalked, faded in color. So if you saw a military vehicle out there on the road, the black color was somewhat turning gray. So what we have here in data created by Army Research Lab is a lot of historical chemical agent resistant coatings. So I will point to the specification requirement is at this point right here. Is 560 megajoules is basically equivalent of 2 years exterior durability in real world testing. So it's an accelerated way to get exterior durability. The pass-fail requirement is at the red line. So the traditional coatings barely passed the specification. Some improvements were made to coatings over the years that got much better when we started getting into polymeric flattening agents and liquid coatings. The powder coating developed. The first qualified product we developed is right here. The black line is our black powder coating. So we have a delta E of 0.2 after the specification requirement. The pass-fail criteria being 2.5. So we doubled the requirement for the specification, and we were still basically only well below pass-fail. So we're far exceeding the specification requirements for exterior durability. This is a big win. You can see the traditional coatings were up here. So I'll speak a little bit more of the benefits of that, but if you can imagine, if the paint doesn't fade and it retains its durability, then we're repainting less. Again, this data is very important because it shows all the historical CARC coatings that have been sold over the years. And I'd like to point out also we developed 3 colors during this, and The tan product, which is another big color, black, tan, and green, is very much way down in this region for color change. There's hardly any color change when doubling the specification requirements. And the green also, probably the toughest color to have exterior durability on, is still below the specification requirement after doubling the spec. So one of the things I'd like to point out is just, the coating is zero VOC. We've worked on waterborne before, but it is zero VOC. The excellent exterior durability means that there will be less repaints out there, and really, the longer a coating system can last, really the more environmentally friendly it is. We're in the business of selling paint, but if the paint system can last longer, it's a big win for the depots. The last thing we need to do is have the paint as a failure on a military asset. The powder coating does use a powder primer, and the powder primer really is a high chemical resistant, highly tightened cross-linked primer. So the fact that we put a powder coating primer underneath the powder coating top coat really adds to the corrosion protection also. It's just, if you buy furniture, metal equipment, everybody promotes powder coating tough. So one of the key things we point out, that just the powder coating system in general, it's baked on there. There's a baked on coating, so it provides a very durable, hard, tough coating. And again, we have developed this in 3 colors. So these 3 colors basically represent 98% of the business that's out there in cart. And I would have to say that not only did we develop something that was environmentally friendly, but I think the statement being as we went in cart from solvent-borne coatings to waterborne coatings, it was noted that performance does not need to drop off just because you're environmentally friendly. We've even gone to zero VOC now, so more environmentally friendly coatings, and the performance has even gotten better. So it's very rewarding to have generated not just something more environmentally friendly, but something more durable and ultimately something that will last longer. We want to say just the technical approach was very successful in meeting the end requirements. There was very much a synergistic effect between the incompatible polymers and the low levels of fillers. So you had to really do both. And Jim Wynn will show many slides that show our incompatible polymers, and then some slides that where polymers were added and where polymers and then the fillers were added. So you'll be able to look side by side how these things work synergistically. You could not get to the low gloss without having both incompatible polymers and the flattening agents. Again, the exterior durability is basically state-of-the-art, leads best in class of anything, and we basically would want to say that we have developed all the key colors that really will complement liquid cart coatings. Thank you.
Okay, thank you very much, Mark. It's now my pleasure to introduce Dr. Jim Wynn. He is a synthetic organic research chemist at the Naval Research Laboratory. Since 2000, he has collaborated with government laboratories and academic institutions to develop novel coatings for military and civilian applications. He holds a joint appointment as an affiliate research professor at George Mason University. Most recently, Jim's expertise in research at the Naval Research Laboratory has centered on the development of novel polymeric coatings and the synthesis of novel actives for a variety of applications, such as de-icing, easy cleaning, signature, and decontamination. Jim has 16 patents and is the author of over 83 peer-reviewed publications. He received his PhD in chemistry from George Mason University in 2000. Jim?
Thank you. So I'll start on slide number 27 and reiterate some of the things that Mark just said. But knowing that we are extremely limited on the amount of pigments that can be successfully incorporated into a durable powder coating, we were forced to look at other methods of gloss reduction. So in an effort to seek these other methods, our attention was turned to the binder system and utilization of the phase separation that polymers would naturally give us if we selected the correct combination. And this phase separation ideally would result in additional roughness and give the desired gloss reduction that we wish to achieve for military applications. In slide number 28, we utilized polymer incompatibility. Specifically, we wanted to take advantage of modulation of Hansen solubility parameters. And specifically, we were utilizing polyols by modulating the hydroxyl pendant group, the content. In one case, we were looking at fairly high OH content and combining those with low OH content polyols in order to try to achieve a phase separation or incompatibility. Utilizing the modulating the Hansen solubility, we can exercise control over dispersion, polymer, hydrogen bonding, and other interactions. So this ability to mix and match definitely played into our favor for this application. A very generic structure of the acrylate that we utilized in preparing the polyols from Estron is shown down below, where the R prime and R double prime are aliphatic contents, and the X represents the hydroxide, or in some case some other heteroatom such as a halogen if we so choose to incorporate it. In short, we wanted to ensure that the high and low OH polyols were compatible enough to react, but at the same time we wanted to be able to achieve this phase separation that would be desired in order to form this surface texture or roughness. Slide 29, in order to prove this concept, we took the high OH and the low OH and wanted to demonstrate that indeed those two polyols, when combined with no curative, upon heating would demonstrate phase separation. So we took the high and low OH polyol in a 1-to-1 ratio. We co-extruded it, we ground it, we sieved it to a uniform particle size of less than 100 microns. We electrostatically applied it to Q panels as one would a typical powder coating, with the objective to show that the high and low OH without the curative would phase separate. We heated, in this case, for 1 minute at 400 degrees Fahrenheit, and then quenched it by placing it upon a cold surface. This optical image shows that indeed phase separation did occur in as little as 1 minute. I want to point out that the horizontal lines that are shown there are simply the aluminum panel onto which the clear polymer was applied, as these are optical images and we're able to see through the polymeric film. We know that these are polymer domains because the particle size that we applied as the powder through electrostatic application would be less than 100 microns, and as you can see from the scale bar, this is clearly much larger than that. So we are forming polymer domains. And slide 30 is the illustration of where we're seeing increased level and flow upon heating. This is at 1.5 minutes, and slide 31 is at 2 minutes. We see this process continue to flow and level with increased phase separation, and this continues throughout the heating process. In slide 32, you can see a greater degree of coalescence and this continued phase separation as would be desired to achieve the goals of that Marc alluded to earlier. In slide 33, at 4 minutes, you can see the phase separation continues. Notice at this, at no point that I'm showing you are we achieving complete stratification, which is very very desirable, and we feel that that's probably an interaction between the polyol and the aluminum substrate. And finally, at 34 is when I stop. We continue to coalesce without the hindrance of stratification. Next, once we realize that we're able to achieve the incompatibility using the high and low OH polyols, we wanted to turn our attention to what would be required to make durable coatings. In slide 35, we wanted to utilize this incompatibility and cross-link these these high and low OH polyols into a durable urethane system. So in order to do so, we selected isocyanate as our curative because it's frequently commercially available and has been utilized in many commercial applications to cross-link polyols. In this particular case, we used a commercial ecaprolactam polyisocyanate, which will afford the desired urethane cross-linking. We selected the urethane because it was reactive with the polyols and also would afford a very durable chemical-resistant coating. So in addition to that, we knew that phase separation occurs of the polyol. But what would happen once we started to cross-link these polyols with the isocyanates? We knew that we had to be very careful because there was a delicate balance between the increased viscosity that we would observe from the additional cross-linking, but yet phase separation we wanted to incur as well. So increasing the cross-link density, we were able to trap the domains in place, and as you will see, this greatly limited the mobility in the curing process. Slide 36. We needed to confirm that indeed we were able to make a durable film. The image on the left is a laser confocal from a laser confocal microscopy. If you notice the cross, the vertical and horizontal, that's simply a artifact of the stitching software where we stitched the four images together. So it's simply an artifact. So we use laser confocal microscopy as a technique to monitor the surface roughness through root mean square, and this was a very useful technique in it allowed us to predict the gloss or the reflectivity of the coating system. In the graph on the right-hand side, you can see we start off at 1 minute. The root mean squared is with a very low surface roughness, and this is what is to be expected given the fact that we've heated the polyols with the curative at 400 degrees Fahrenheit for only 1 minute. If we then go to slide 37, we see that phase separation continues. At 2 minutes, surface roughness is increasing, but still we have a continuous film. And it's very important to illustrate that we must afford a continuous film that completely coats the surface in addition to providing the topical surface roughness to achieve the low gloss. There's no obvious sign of domain formation in the image as shown, and we believe that at this point that it's still a melt flow process given the even coating of the surface. At this point, likewise, we believe that the deblocking of the protected isocyanate is just starting to occur. On slide 38, at 3 minutes, we see a rapid increase in surface roughness, both in the image shown on the left as well as the root mean square analysis graph on the right. Domain formation is starting. It increased the surface roughness, and this correlates to what will ultimately result into gloss lowering effects through the surface texture. Just quickly flipping through slide 39, you can see as we continue to heat at 4 minutes, the surface roughness increases, albeit at a lower rate. And slide 40, at 6 minutes, we've progressively increased the roughness. And we will increase the roughness, as you'll see in slide 41 now, that up till 9 minutes. We believe that this increased roughness results from the continued reaction and the continued phase separation that's occurred. Overall, we're overcoming the thermal process of deprotecting the isocyanate, the pressures that are involved in the cross-linking or expansion contraction of the polymer, gravity, and any other bulging effects that are resulting in the domain formation. Eventually, we realized that the greater viscosity is resulting from a higher cross-link system, and therefore the individual monomers or polyols are less likely to be able to move to form a smooth surface, as is observed in slide 42. At 12 minutes, you can see a slight decrease in the surface roughness. We believe that this reduction, albeit slightly over the 9 minutes, is the polymer system being locked into place, yet continuing to react or cross-link with the resulting unreacted moieties that remain. And we believe that because this is above the glass transition temperature, that segmental motion is resulting in this slight rearrangement and lowering of roughness. Although we would like to have the coatings, we would like not to observe this reduced roughness over the 9 minutes, we realize that a very well cross-linked system is essential if we're going to achieve the desired chemical resistance. In addition to this, the continuous polymer film and being able to uniformly coat the surface is highly desirable. In slide 43, in order to confirm what we believe and had observed through surface roughness measurements, our attention turned to thermal analysis. It was specifically TGA. We can see on the right side that we start off the polymer with a glass transition of approximately 60, and this is very consistent with commercial powder coatings in that a relatively low glass transition is required to ensure thermal stability on storage. However, as we start to cure the polymer coating, we see a second glass transition appear at approximately 3 minutes. This appearance of the second glass transition temperature confirms the domain formation as we originally believed. And this continues to increase the glass transition past 8 minutes, which also confirms that we have continued cross-linking systems even after the domain has formed, which is essential for the durability of the coating system. On slide 44, any real coating system, as Marc alluded to earlier, must require pigments. In order to determine the effect of the addition of the pigments with respect to what we've just seen previously, the clear coatings without the pigments and fillers, we decided to turn our attention to the addition of the fillers, in particular here, carbon black, to result in a black coating system. On the left, we see the laser confocal at 12-minute cure of a clear system without the addition of pigments and fillers. And on the right side, we see a 12-minute cure of the same polymer system, but this time incorporating pigments and fillers. You can see that there's a dramatic increase both in visual and in surface roughness, as noted below, and this is absolutely necessary and essential for the down gloss of these coating systems. And the root mean square on the lower left for the clear shows 0.34 microns, where the pigmented system on the right side is 2.7. We've demonstrated at this point the incompatibility of the polyols alone without the curative to form the domains. We've demonstrated that in clear systems we can cross-link them to result in rough textured systems, and now this illustrates that through the addition of pigments that we can even increase further the roughness of the coating system and result in a lower gloss system. Slide 45, we wanted to utilize the same technique as we did earlier with our ability to follow the reaction through roughness formation, this time with the addition of the pigments. On the left side is a continuous film on a surface at 1 minute cure, and on the right is the 12-minute cure. You can see that there's a dramatic difference in roughness. If we look on the graph on the right side, we see that at the line at the bottom illustrates the earlier presented incompatible polymer system that has been cured and roughness analyzed using without pigments, as compared to the line at the top is with the pigments and fillers. And you see a dramatic enhancement of roughness with the addition of the pigments and fillers, and this rapid change, rapid variation from the coatings without the pigments and filler really is illustrated at the 2-minute cure process, and typically maxes out at about 4 minutes into the cure process. And although it does decrease slightly in roughness after the 4 minutes, again, this is a necessary evil to sacrifice slight roughness of the texture of the surface interface in order to achieve a very cross-linked durable system, which is essential for the chemical resistance. Slide 46 is how do we quantify the effects, although we can visualize these and look at the roughness. Starting with the left side, we have the low hydroxyl, the low OH polyol being cross-linked, low hydroxyl only, no blends, with the pigments. And you can see on the very left side, you see the root mean square of 0.13 micron, so a relatively smooth surface, and with 66 gloss units, which really confirms that it's a very high gloss system. In the center is a high OH polyol that is cross-linked. As you can see, it's slightly more roughness with the numbers at the bottom, 0.4 microns, and we're down to 16.5 gloss units at 60 degrees. Finally, on the right side, you can see the blend of the two, 1-to-1, low OH and high OH cross-linked. You can see that the surface roughness significantly increases to 2.9 micron, and the gloss units is down to less than 1, which is highly desirable for a low gloss military coating. So clearly there's a synergistic effect of the addition of the pigments with the polymer phase separation, and that's how we've been able to characterize this, where the flattening agents, the fillers alone, were not able to achieve that. In slide 47, now that we know that we're forming the domains as confirmed by surface and thermal analysis, we really wanted to characterize and identify the composition of the phases that were being observed. In order to do so, we cross-sectioned the coating, we embedded it in a resin system, and we polished it for Raman analysis. And the image in the upper right-hand screen is a optical image of a 150 micron thick film that has been sectioned and polished. You can see that within that red circle, there is a visible domain within a continuous phase of polymer. We took this sample and we were able to acquire Raman spectra of both the domain, which was inside that sphere, as well as the continuous phase, and those spectra are presented on the left. The top is the encapsulated domain, so the interior portion that was highlighted in the red circle, and the continuous phase is the spectra below. Notice that they both have peaks at 1600. However, the continuous phase of the polymer matrix has a nice handle in that it has a 1632 reciprocal centimeter. This serves as a nice handle and has allowed us to perform a mapping of the same sample as is illustrated on the bottom right. The map is a intensity mapped at 1632. You can see the top and the bottom, the outer edges of the coating system, and you can also see within the domain itself the absence or the very low concentration of 1632. I want to point out that as you go from the center of the domain outwards, you can see that there's a gradient. So it's obvious that there's a gradient in composition of the polymer out to the continuous film, and the continuous film is relatively consistent. So once we had this mapping, once we had the spectroscopic handle at 1632, we felt that we had the tools in hand to identify the composition of both the domain and the continuous polymer matrix film. And that's what we did in slide 48. If we look at the spectra on the right side, we elected to look at the individual resin systems first with the low hydroxyl polyol only, and we see that we had the two peaks, especially with the peak showing at 1632. The high hydroxyl resin alone, the control, did not have the absorbed at 1632. When we analyzed the continuous phase and the encapsulated domain phase, the circular portion that was highlighted in the previous, we see that we have a direct correlation where the high hydroxyl polyol content is forming the majority of the composition of the encapsulated domain, whereas the low hydroxyl polyol is forming the preponderance of the continuous phase. So therefore, in doing so, we have not only mapped but utilized a spectroscopic handle to identify the components of the film and have demonstrated that indeed they will separate and phase separate during the cure. So finally, in slide 49, to recap some of our key findings, we've demonstrated that phase separation results and surface roughness is demonstrated both in clear and in pigmented films. We've demonstrated a synergistic effect of domain formation and pigment incorporation. And finally, we've been able to identify the actual domain themselves and their composition and be able to associate a low or high OH with the corresponding domain and pigment and continuous film. And that concludes my portion.
Wonderful. Thank you so much. And at this time, I would like to remind our audience to submit questions by using the chat box on the left-hand portion of your screen. We have received a number of questions on our first presentations that Marc or Jim will answer. And Jim, the first question is for you and follows what you were just talking about. The audience noted a reliance on polarity differences to provide phase separation in the coatings. Do you anticipate or have you observed problems in morphology stability with solvent resistance or cleanability where solvents might interact differently with each of the domains?
It's a good question. No, we really have not. I think we were fortunate to start off with a fairly robust system that yielded a very cross-linked tight network. And as a result, the resistance to chemical solvents and so forth has not been a problem. Marc may add some previous work comments on that if he wish.
I would just say that, yeah, individually there's a tremendous, when the two resins are applied individually, yes, there is definitely, attack of solvents to the low OH, the continuous film. However, when they are put together to make these incompatible domains, it is somewhat surprising, but when we do the resistance to that, the domains stay intact. There is no destruction of the coating system whatsoever. So we're getting a very, the solvent is not touching anything in there. So we keep the morphology.
Okay, thank you very much. The next question is for you, Marc. Are agent data available for these coatings?
We would have to take that offline. It's probably not public information, but we have obtained, yes, the data from that. So I would say that maybe there was some type of coding that afterwards, if the question would want to approach me, that we would have to be very careful with that data.
Okay, thank you. And to the audience, the speaker contact information is in the slides that the audience members will receive. Next, please discuss the type of test you conducted to evaluate live agent resistance. Did they include things like time to absorption or contact angle? Marc, we'll start with you, and if you want to pull Jim in, feel free.
Yeah, I would say that the simple answer is that the requirement is specified in MIL PRF 32348. So that it is the standard chemical agent test done now at this specific time. We are qualified, so it is all spelled out, public information in the specification. Basically done, data is run back through Army Research Lab to confirm that all data is basically run with a proper control. It is run through, this is the real deal. This is how agents have been run for the past, 30 years for chemical agent resistant coatings. So it's the same test that we've been running with liquid coatings. So it's in the specification, I think would be the best answer.
Okay, thank you. The next question is, with the accelerated weathering, did the gloss change with exposure time? Jim, I'll start with you on that one.
I think I'll have to pass that to Marc.
Yeah. I mean, these are dead flats, so no, the gloss did not change. There is a gloss requirement to not go beyond the spec requirement. I believe it's actually not go higher than 0.05 units from where it was. So if it was 0.5 at 60 degrees, it cannot go above 1. So we met again, in MIL PRF 32348, there are gloss change requirements in there. So gloss and color are both requirements. So we meet all the requirements of that. So it just seems very stable, but the interesting thing is we are starting dead flat. So we are staying dead flat.
What is the expected shelf life for the coating?
1 year is our shelf life.
Thank you. And how would you depaint the coating, especially outside the line of sight?
Again, I'm going to refer back to how Kirk is typically depainted. Blasting is a very typical method. Sandblasting is probably the one of the more environmentally friendly ways to do it. So part of it is just it needs to fit into the standard processes that everybody does now. So it blasts just like it is removed by typical methods that Kirk is removed, which I would have to state is, blasting if it's not sand, it's other medias. Is a very big part of removing it.
Okay. And can the newly developed powder coating be applied over existing military specification liquid epoxy primers?
I will say on that one, no. That's one of the learnings of this is that basically, as I spoke to earlier, it was basically that was the goal to begin with, is to apply it over liquid-based epoxy primers. But what we and other coatings companies who are developing this coating have found out that basically the liquid epoxy coatings outgas when you put the powder coating on and bake them. So they produce inferior film. So it really makes sense and is a requirement to use a powder coating under the powder coating top coat.
Okay, thank you. And is there a way to apply powder coatings on non-conducting substrates? Mark, I'll let you take the first shot at it.
I'm not the biggest application expert to answer that, so I'm trying to think of an example where you would want to, but I guess I would say that the powder caulk top coat is applied over the powder caulk primer, which is a non-conducting, not substrate, but dielectric film. So it does get enough of a charge from there. And I think there's some standard practices in the art of heating parts where you might want to apply it. But it's an interesting thing that I don't think we've done a whole lot into.
Okay. And we have just one last question before we move on to Beth Ann's presentation. That is, how effective are chemical paint removers on the cured powder coat? Was this tested on an aged coating system?
I would say I don't have the data that it was tested, but historically, again, I would have to say that it should work. Historically, other caulk coatings have been removed after aging, so I would see where this one would be different.
Okay. Thank you very much, Mark and Jim, for the excellent presentations and answering those questions. If our audience has more questions for Mark or Jim, please do submit them. They will be back at the end of the webinar to address more questions with all three speakers. And the next part of the webinar will be presented by Dr. Beth Ann Pearson. Beth Ann's knowledge in the coatings industry is coupled with 20 years of experience with coatings technologies and chemistries. She currently works for Sherwin-Williams Product Finishes Division as the Global Military and General Industrial Manager. She is a member of numerous professional organizations, including the American Chemical Society, National Association of Professional Women, Polymer Sciences Society, and Federation of Societies for Coatings Technology. She has received multiple professional honors and leadership awards. Beth Ann has a Bachelor of Science degree in Chemistry from Harem College, graduate degrees in Physical Chemistry and Polymer Science from John Carroll University, and a doctorate in Global Business and Leadership. Beth Ann?
Thank you, Jennifer. Following up on what my coworkers and teammates have developed, we've talked about the defined need for powder caulk technology. Then we've transitioned it over to the concept and how we identified it, to the development of a product, and now I want to take it through how we're commercializing that, the actual product into application onto military assets. So if we take a step back and just really look at what are coating requirements overall, powder coatings, caulk powder itself, or even liquid coatings, the number one critical aspect that should be number one in everybody's mind is the survivability of our war fighters. So what are we doing to protect those who are serving and giving their time to protect us? Secondly, and I say a far second, but obviously critical, where we can really begin to have an effect on it, is the durability. And when I say outstanding durability of the coatings, when we start to specifically look into caulk, be it powder or liquid, this durability extends beyond just color and gloss, or it's an expansion of that, I should say. If anyone's not familiar with caulk coatings, and I should have asked that from the start, chemical agent resistant coatings have two specific aspects that really differentiate them and identify them as actually weapons of war. These are coatings that are controlled by the government under ITAR regulations. One is the color is identified that has a specific IR signature. An easy way to say that is it's protection from detection from enemy forces. So every color has a specific IR signature that is unique to the color. The second aspect is that they have to be easily decontaminated from chemical and biological warfare agents. So when I say durability, it's critical that we don't lose that color, we don't lose that gloss, or the coating isn't breaking down because we lose the two critical aspects that really make it a Carc coating. Coupled with that is the excellent corrosion resistance. $23 billion is the amount that the Department of Defense identified as the cost of corrosion to military assets in a single year. $23 billion coming out of all of our pockets as taxpayers, as American citizens, that could be applied to other means of government services and protecting or providing higher quality care needs, programs, whatever it is, for our military involved members. So obviously corrosion is important. And I always say the two buzzwords right now are lean and green. Lean and green. So how do we do it most cost effectively or process effectively, and what green initiatives are identified? Obviously water technologies. The more solvent we can get out of our coatings, the more we can go to water, the better it is for the environment. Elimination of heavy metals. Perfect example, we went from chrome 6 to chrome 3. The drive now is to have chrome-free technologies. Lower VOCs, less solvent emitted into the atmosphere, coupled with the choices we use, exempt solvents versus non-exempt solvents. And then not listed because it's least important, but listed because we're going to move it that way, are powder coatings. So having the use of powder coating means that we have less waste to the environment. That being said, why was there an identified need for a powder technology? Why would an applicator, an OEM, a tier supplier even be interested in using powder technologies? Well, I said lean and mean and green, near zero VOCs. Some people say powder coatings have zero VOCs admitted to the atmosphere. I'm going to say near zero because there is a risk, and I don't want to mislead, there is a risk that any powder technology, any resin may have a minimal amount of solvent still remaining into it. So it's virtually zero, but to be absolutely correct and upfront, it's better to actually say near zero VOC. With powder coatings, you can get higher film builds. If you exceed the film build of the performance of a rheology-controlled liquid coating, you start to see sags, or you may see pops, or you'll see runs and drips. With powder coating, when's the last time you really easily see a sag or a drip coming off of the part? So you can get higher films typically with a powder than you can with a liquid. And you can do it in a single coat application. It's not, you don't have to do the flash time or through the bake or cycle time. So a single application saves time. You can get specialty effects. When's the last time in a liquid coating, if you see, for example, a textured effect, it's typically not a good thing. But when you see it in a powder, it's intentionally formulated to be applied that way. 95% recyclable. So again, lean and green. By saying they're up to 95 or even greater, some will claim 99% recyclable, that's under the assumption that the powder is, for example, in the application area, color controlled. So you have to make sure that you're recycling and recovering colors, or you're limited with colors so you don't mix, or that the storage conditions are appropriate. Think of powder coating as if you have flour in your kitchen in your home. If you have powder, this powdery flour, and it's stored in a damp environment, or it gets mixed with water or high humidity, right? You get the clumping in the wet situation. You're going to get the same thing with powder coating. So they do have to be handled carefully in controlled, in humidity and temperature controlled environments. Carc powder is no different than a standard powder for how that would be handled. You know, the same, resistant to chip, resistant to scratch, and corrosion protection. So whether we're talking about a powder or a primer, there are ways and means that powders can be applied. For example, Faraday cage effect with application allows the electrostatic wrap so that those corners of a part that are difficult to coat or difficult to achieve the correct film build on is much more effective to do with a powder coating. You're not getting too high of a film where you're getting dragged. You're not getting too thin because you're not getting enough electrostatic wrap to it. So powder coatings are known for improvement with that. So when I talked about the $23 billion cost, our Congress enacted a legislative requirement where sitting within the Office of the Undersecretary of Defense for Acquisition, Technology, and Logistics was created an Office of Corrosion Policy and Oversight. So the majority of the focus of this office is to prevent and mitigate the corrosion of military equipment and military infrastructures. In other words, to decrease that $23 billion cost, to get the number smaller, to put the money back where it should be. So if I take it back to the costing or to the actual purposes, I talked about application efficiencies. So I talked about wrap, electrostatic attraction, Faraday cage effect. With powder coatings, you get increased transfer efficiency. The benefit to that is exactly what it sounds like. The paint that you're trying to get on the part, you get on the part. If you don't, you can recycle it and put it on the next part that comes around. So you get higher transfer. It's not going up the stack. It's not going out. With liquid technologies, someone who's running a liquid line, you have to worry about insurance, for example, flammability, because you've got the solvents in your facility. And I'm not saying, I don't want to mislead and say that there isn't insurance that gets covered for security and safety, but I'm saying you're going to have lower insurance costs because you don't have to worry about the flammability. You're not emitting VOCs out into the atmosphere like you're doing with it. So you're getting more efficient use and lower costing. Lower material cost means you get less material used. Lower unit cost is an overall wrap better for the environment. So where did we end up? Marc and Jim had both talked about where we started, how we moved to, so our final product. The fast cure means fast production. So a typical coating, if you're looking at, for example, a military coating, then it's a 250 bake for 30 minutes. Or if you're looking at an ambient cure condition, it can take 4 to 7 days or up to 10 days depending on the technology you're using. Fast cure means fast production. The technology that was developed through this program requires a 10-minute bake at 400 degrees max. So that's metal temperature. It's important to note that that is not 10 minutes at sitting in an oven that's set at 400 degrees. That's 10 minutes of the metal temperature that the coating is applied to. We need that 400 degree period to ensure that we get the proper cross-linking for the full cure. That way when the paint is taken out, you can be assured that the full cure of the technology is not a semi-cure that then becomes fully cured once it's applied to the asset, or that must sit around and continue the reaction for days. After 10 minutes, the product is fully cured. Marc talked about through the development of the program using MEK, methyl ethyl ketone solvent, rubs as an assurance that correlated back to cure. And that's how we were able to come up with where we are and where we've been. The product maintenance. So again, once it's cured, you don't have to leave it sit around so it can go. So it's ready to go right out of the gate. So it talks about the products have been manufactured or ready to go. Where do we move from here? Well, current status is actual commercialization. And how I get to that is you can see this was the slide you're looking at is simply a picture of the coating application as we were managing it. Colors were developed. Over 95% of the military assets applied in the last year are actually consisting of the 3 primary camo colors, and I'm not including brown in the camo. So if we look at TAN 686A, and for those not as familiar with the military lingo, that's actual federal standard number 33446. And any number that starts with a 3 in a federal standard means that it's a flat or it's a lusterless color. So TAN 686A, green 383, which is federal standard 34094, or black, and the Army Research Lab, the specification allows for aircraft black or black to be used interchangeably. So when you see Federal Standard number 37030 or Fed Standard 37038, those two colors may be used interchangeably. And that is the third color that was developed for testing. Before a product is taken out for commercialization, we want to do our homework and ensure that we're ready to have it commercialized. So there's two steps to commercialization. One is, can the product actually be scaled up? What it looks like in a 1-gallon container on the bench. Am I going to get the same product when I look at it as 3,000 gallons in a reaction blend system? Second is, does that paint then apply the same in a laboratory environment as it does in an application center, as it does on a customer line? So that's the development for commercialization that I'm talking about. For this case, we employed design of experiments, DOE. We applied statistical analyses to be able to understand and predict the behavior of the coating. So there are different types of statistical experiments that allow for this to happen, and we employed screening designs as well as surface analysis designs. These DOEs allow us to really understand the robustness of the system. If you think about defining the edges of the box of how the product is going to scale and then how it performs. And you identify the critical aspects that need to be studied. So various substrates. We don't want to limit it to just look at, for example, cold rolled steel or blast it. It's looking at any of the substrates that we expect the coating to potentially be applied to in the field. The different primers. Questions came up and Mark was talking about liquid primers versus powder primers, and this is one way that was identified with which ones, what the mil spec identifies and how that works in real life. Top coats for recoatability. So powder over powder, liquid over powder. How does that work? The cure conditions, and when I say cure in application conditions and methods, we want to understand how we can apply this coating at 100 degrees in Mississippi, for example, in the middle of August, or in Iceland in December, and understand how the limits of the coating the limits are, as well as how the film thickness. We all know in an ideal world, the military specification has a specific film thickness identified. We want to understand and recognize that those ideal conditions aren't always followed. So if we go above film, below film, what's the maximum and what happens once we get outside of that range. So these statistical designs I'm talking about, we verified the gloss retention. As Mark had mentioned, the gloss is very low, and how low do we go? The adhesion, the physical properties identified in the mil spec. So there's several. And flexibility and agent resistance and solvent resistance, how all of that works. Recoat of liquid and powder primers over the Kark powder. What happens with overbake? And a perfect example of that is we said you need a minimum of 10 minutes at 400 degrees metal temperature to achieve. We actually had a study where we left the powder, the coated panels, in for 16 hours at 400 degrees. So if an oven shuts down and you go to lunch in a production line, what happens? And saw only a minimal color drift, and the drift was still within the allowed range of the specification. And finally, that's the result of how our recommendation of 2 mils of film thickness. So the result of this, basically to summarize, is we have developed a Kark powder that maintains all the physical appearance and application properties that are defined and under the conditions under which it can be applied. So that's the first stage of commercialization. The second stage is the application part. Again, it may apply in an ideal condition in the laboratory, and even being able to vary conditions in a lab, how do we take that and apply it into a real life situation? For those who aren't familiar with STAR 4D, in Cedar Falls, Iowa, there is a location, an application center called the Spray Technique Analysis and Research for Defense. Again, it's known as STAR 4D, who have application equipment as well as experts in military coating technologies. So they know the market and the different challenges and how the coatings can be applied, the different substrates that can be applied, and all of the different conditions. So we sought their assistance. We took a finished prototype, laboratory and production sample, and had this analyzed at Star 4D. In other words, have at it. We handed them the paint and say put it through its posts. And we did the same thing with it to really understand and ensure that we were not trusting or testing the product on our customer line. We were doing our homework before it actually got to the customers. After the Star 4D analysis, one of our partners was Albany, the Marine Depot Maintenance Command Center from Albany, Georgia, the Marine Corps base. Steve Allen is our identified partner, and we worked with Mr. Allen to take the sample and actually look at it on his customer line. So that way we went from concept of working in a laboratory to an application center to an actual customer line to be able to adjust. These are not pictures that were painted at Albany, but this is commercial product that has been sold and is currently being applied. So you will see this is our Kark green powder on a military trailer, commercially sold, now out in the field. A different piece of equipment, again, this is Kark powder. We have a customer who was kind enough to let us show where we're actually selling this in real life. This is black, Kark black, again being applied to military maintenance. And the black in a real life application setting. I just wanted to give you a little bit of flavor to show you that these technologies are indeed verified, validated, and commercially available. So I have to sum it up. I say mission accomplished. So the call for need was identified. It had been marketed in the industry for several years, kind of like it was being chased after as a desire, but had not been successfully achieved. There were a lot of prototypes that I've seen in the market space that are not so attractive, and that's the beauty of something like a Serta PSTS program, is it allows, in some cases forces, the priority to a project for a defined need to actually perform the hardcore research and development to learn the technology and take the time to really understand what we're developing. As a result of this, Sherwin-Williams, through this program and working with our partners, has successfully developed a Kark powder top coat technology that is approved and is listed by the Army Research Laboratory on the QPD. Slide's a little bit out of date. We now have qualified products in the black, the green, and the tan. The scale-up to manufacturing has been completed. The platform technology has been completed, and there are commercial sales currently ongoing for the past several months. The platform technology, now that it's understood, is expected to be leveraged for future products that we're currently looking at. It's been validated, and then there's discussions on how this will transition to broader markets within and even outside of the military. So I hope that gives you a little bit of a feel for where we are from a commercialization standpoint. Sherwin-Williams, I'd like to acknowledge our team, and as Mark started off by saying, we had a very strong team that worked together. From my organization, Mr. Marc Whitehead was the primary investigator leading it, worked with Mr. Mark Walker, Edmund Mann, Don Gruska in the laboratory, Dr. Morgan Sibold from our Sherwin-Williams team. From the Naval Research Laboratory, Jim Wynn gave part of the presentation. His associate Spencer, now Dr. Spencer Giles, worked with us. From the Army Research Lab, efforts were led by Mr. John Escarzega for his technical input, coaching, and support, and idea development, as well as Mr. Daniel Pope, who is on John Escarzega's team for a lot of the testing and supporting documentation and technical expertise. I talked about Steve Allen from the Marine Depot production plant at Albany, Georgia. Estron Chemical was our industry partner for resin development, led by Dr. Robert Auerbach and his associate Mike Miller. And finally, our academic partners working with ONR heavily on commercialization and testing from Stony Brook University in New York was Dr. Clive Clayton, and again now Dr. Nicholas Heller. We want to recognize all of our team members. So with that, Jennifer, I'd like to turn it back over to you.
Thank you so much, Beth Ann. We had a question from the audience about the QPD number. Can you provide that?
So for anyone who doesn't know, any technology that is tested and validated by the Army Research Lab, or in this case it's the Army Research Lab for any technology, whatever the controlling entity is, be it NAVAIR or NAVC. In this case, the Army Research Lab has a specification. They test the product against it, and then they issue a qualified product database. The product is listed on that, which means it can then be applied to any military asset. Sherwin-Williams is listed for each of the 4 products. If you actually want the numbers, I can give those quickly. Our black product is Q2203. Our green, and I should say the product code is U as in under, B as in boy, S1-800004. The green is Q2224. Product code is U, G as in George, S as in Sam 1-80000. The last digits are all 5 numbers. And then the tan is Q2265. U, H as in Henry, S as in Sam 1, again 80000.
Okay. Thank you very much, Beth Ann. Next question, was a quantitative test used to qualify the top coat adhesion?
With a quantitative test used, I'm going to say yes in a couple of different ways. So quantitative testing, and Mark, if you want to jump in if you're still here, testing is conducted as a standard, so adhesion testing if it does or does not stick with testing. We also took panels and looked at them microscopically to understand where the loss of adhesion occurred, so whether it's cohesive and to which layer, and to understand the degree of loss. So top coat compatibility was conducted as standard methods.
Yeah, I would just add that, that again, we were passing specification requirements, which is like ASTM D3359 cross-hatch adhesion, and needing to pass a 4B. So that's basically the quantification. There's not been any numerical adhesion values associated with it. But I think what we were able to put layer upon layer and boosting film thickness up high when putting brown or black on top of green on top of primer. So we have multiple mills, which typically challenges adhesion, and we still have very good adhesion with crosshatch adhesion. So there was a lot of adhesion testing done via the crosshatch adhesion test.
Okay, thank you very much. And we do have Mark back on the line, and we'll bring Jim back as well for a few questions. The first question that we have, and we'll direct this first to Mark, Beth Ann and Jim, feel free to jump in. What is the most challenging technical hurdle that you needed to get past to develop this product?
This is Mark. So I think that the challenge, we've always been able to produce low gloss powder coatings, but the chemical agent resistant coatings add even lower gloss than is typically used in commercial applications. So getting stable low gloss with a smooth appearance that doesn't look like sandpaper, a huge amount of texture as that has been used in low gloss coatings. So getting a low gloss with an acceptable appearance, and then you combine that with the chemical agent resistance, because as you flatten it, then you make it more porous. So combining low gloss with chemical agent resistance, and then ultimately the exterior durability. So all those combinations. But a lot of it comes back down to low gloss and chemical resistance.
Okay, thank you. And Beth Ann or Jim, would you like to add anything to that?
I can say from a commercial aspect, as Mark said, the low gloss is definitely to have something that's low gloss and stable. There's a lot of low gloss powders, but they they're maker used, so they don't last as long. So that's why you see there's a lot of non-military applications that call or have an interest in this, but the market hasn't been able to really answer the call for.
And I think this is Jim, from a scientific technical aspect, it was very challenging ascertaining the mode of action or elucidating the mechanism for the domain formation. But it was very fruitful in the end.
Okay, thank you all. The next question is, are there next generation cork powder technologies expected? And how will their requirements differ from this one? And we'll start with Beth Ann.
We're always looking into research of what we're going to do next and what we're going to do best. So I would say there's a Gen 2, sure, and the requirements will be defined obviously by the Army Research Lab. But they're very good on working with industry partners and other DoD entities to really understand what can be improved on for what we have. So for example, bake temperatures being even lower than 400 degrees has been a potential interest. The way we test for chemical warfare agent efficiency may be a question in how to make that even tougher, or with the challenges we're facing as a world today, chemical agents are becoming more aggressive and are changing. So as the world evolves into a more, unfortunately, terroristic approach, what is that going to bring down that we need to make all of the coatings more improved upon? So I would look for that to be coming. So anything you can do, lower bake, compact systems, meaning take a short step out somewhere. So lower bake, faster bake, thinner films, and more protective.
Okay, thank you. Marc or Jim, anything to add?
I would just add that I think we've already begun introducing even more chemical resistance into these systems. So using primers beyond what is in a specification, metal-rich primers, sacrificial primers. So we have powder systems, with metal-containing primers that have already been looked at by, for instance, the Marine Corps as like the next gen, basically upping the exterior / corrosion protection. So that's in process.
Okay, thank you. We have one last question from the audience before we wrap up. The question is, with a cure temperature of 400 degrees Fahrenheit, there are some components that this product cannot be used on, like magnesium transmission housings with steel ballistic liners. So is there any effort to develop a powder coat that can cure at a lower temperature?
So I will say that there is an interest, and that question has been discussed. So it's not an easy process to develop that, but you're starting to see lower bake powder temperatures and higher gloss coats as an interest. So it's definitely a point for consideration, yes.
Yeah, I would add during the efforts, the 3-year efforts of this, we definitely put efforts toward doing that, and we were basically, not able to at that time develop a lower temperature than 400 F. I would add that sometimes equipment such as IR ovens allowed us to get good-looking coatings at 350 F. So let's not forget the engineering aspect of some ovens that might bring something in there. But aside from that, too, in the general industry, powder coatings are always looking for lower temperature cure. So there is efforts within Sherwin-Williams to continually monitor the technology that's out there.
Thanks. Thank you very much. And with that, I would like to thank all 3 of our speakers, Marc, Jim, and Beth Ann, for the presentations today. And our next webinar will be on Thursday, May 18th, and it will be on high-resolution site characterization at chlorinated solvent sites. The webinar will feature Mr. Murray Einerson of Haley & Aldrich and Dr. Andrew Jackson of Texas Tech University. Registration is already open for this webinar, so please visit the Serta and ESGCP webinar webpage to register for this and all the other future webinars. And before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. And we would appreciate it if you would please take a moment to complete the survey that will pop up on your screen at this time. And this concludes today's webcast. Thanks again to our speakers and thanks to our audience.